Hi everyone, today we are going to learn about real numbers. Let's define real numbers. Real numbers are the combination of rational numbers and irrational numbers. Children, you have come across these two words in class 9. So let's recall the definition of rational numbers. You have read it. If your number is written in the form, or if your number is expressed in the form of p by q, where q should not be equal to 0, then it is your rational number. Children, your even number, prime number, composite number, integers, all of them comes under the heading rational numbers. Now, I am going to add up one more definition to rational numbers. If your decimal expansion is terminating, that is, if let's suppose it is coming out to be this, it is terminating, that means it is ending. If your decimal expansion terminates or ends up, then also it can consider as your rational number. Or if it is non-terminating, but recurring and recurring. What do you mean by recurring? Recurring means repeating. Let's suppose your decimal expansion is not terminating, it is not ending, but it is repeating and it is going on and on. That means non-terminating, that means it is not ending anywhere, and the terms are repeating. It's repeating. Alright, so look here, 2.327, 327, 327. For example, I can take it as 2.77777. So this is non-terminating but repeating. That's why I can call this number also as rational number. And in class 9th, you have read how we can convert this non-terminating and repeating expansion in p by q form. Now, what do you mean by irrational number? If you cannot represent any of the term in p by q form, then it is known as irrational number. So, if you cannot write it in the form of p by q, then it is an irrational number. Secondly, I am adding one more definition to it. If it is your non-terminating, if your decimal expansion is non-terminating and non-repeating, then also it can be said as irrational number. For example, if I take it as 2.371045 and it is going on and on. So it is non-terminating, that means it is moving on and on, it is not stopping, it is not ending anywhere, and the numbers after the decimal are also not repeating. That's why this number is said to be as irrational number. Now in this chapter, first of all, we have Euclid's division lemma. Euclid's division lemma. But this year, board has deleted this topic from your syllabus. So we are not going to do this topic here. Second topic, we have the fundamental theorem of arithmetic. It is quite important theorem. The fundamental theorem of arithmetic. And it states that every composite number can be expressed in the form of product of prime factors. That means if I have say 12, so I can find out the factors of it. 2, 6, 2 into 3, 3 into 1. That means factors, prime factors of 12 are 2 into 2 into 3, and it can be written as 2 square into 3. Yes, of course, here order doesn't matter. This can be done like this. It can be done by 3. 3 into 4 is 12, 2. So here your fundamental theorem of arithmetic says that every composite number can be expressed as a product of its prime factorization, but order does not matter over here. And of course you will get unique prime factorization. That means every time when you are factorizing 12, you will get 2 2s and 1 3. Either you are doing it this way or you are doing this way. Then also you will get 2 2s and 1 3. Here also 1 3 and 2 2s. Here also 2 2s and 1 3. So you will get unique prime factorization of a composite number. So this is all about the fundamental theorem of arithmetic. We have one more formula, children. If you have two numbers and if you are finding out the LCM and HCF of two numbers, then you can verify it by the formula first number into second number. That means the product of two number will be equal to LCM and product of LCM and HCF of these two numbers. So this is an important formula which we are going to apply in the questions, where out of these four, 3 strings are given to us and we need to calculate the fourth one. Let's now see the questions of exercise 1.2. Here it is given, find the LCM and HCF and verify it. So the two composite numbers are given to us. Let's find out their prime factors. So let it be 2. 2 2s are 4, 2 5s are 10, 5. Again I can take it with 5, 5 5s are 25. This can go with, let's suppose this is 17 3s are, this is 3 1. You can take 3 first, you can take 2 down, but every time you will get unique factors of it. Let's do it for 92. So let it be 2. 2 4s are 2 6 are 2 2s are 2 3s are and 23. So it is 23 1. So I am getting here 510 equal to 2 into 5 into 17 into 3. And 92, the factors of 92 are 2 into 2 into 23. If I want to find out HCF, then I will be taking common. Here 2 is common, then nothing is common. That means your HCF is 2. When you want to find out LCM, then you have to take the common value. So let's common value, that means 1 2 out of it, and then you need to multiply all the rest of the numbers with each other. So I am writing it as like this. So this LCM will give me 2 3 4 6 0. Now the next part is to verify it. So for verification, we know first number, this is I am doing verification. So for this I know product of two numbers should be equal to product of its HCF and LCM. So your first number is 510 into your second number is 92. Your LCM is 23460 and your HCF is 2. You just multiply them. 6 2s are 12, 4 2s are 8, 3 2s are 6 2. And by multiplying these again, you will be getting it as equal to 0. If these two comes out to be equal, that means verification is done. If your question is given like this, given that HCF is equal to this, that means this is your first number, this is your second number, and HCF is given to you as 9. So HCF is given to you as 9 and you have to find out here LCM. So if I know 3 of the things out of these 4, then I can apply this formula, one number into second number equal to HCF into LCM. So I'll be writing here 306 into 657. My HCF is 9 into LCM. Now if I want to find out LCM, I need to take this 9 down because this is in multiplication over here. So let it be like this, upon 9 equal to, and on simplification you will get it as 22338. Children, if you are given with this kind of question, check whether 6 raised to power n or 4 raised to power n or any number raised to power n can end with the digit 0 for any natural or number or not. Then first of all you need to find out the factors of this number. So 6 can be written as 2 into 3 raised to power n. But children, a number to end with digit 0, it should have factor as 2 and 5. So here 5 is missing, 2 is already there, but 5 is missing. That's why this number cannot end up with 0. So I will be writing, therefore I will be writing 6 raised to power n cannot end with digit 0 because it, or I can write because factor is not of the form 2 raised to power n into 5 raised to power m. The number to end with 0, it should be in 2 raised to power something into 5 raised to power something. If 2 and 5 are the factors of the given number, then we can say it can end with digit 0. Otherwise, it will not end up with digit 0.